The final section of Chapter 1 deals with a powerful set of ideas called counting techniques, and these are going to help us answer questions to do with probability, where the sample space is really large and there is a great number of outcomes. So what we've been doing in the past is actually directly figuring out all of the outcomes. But if you've got hundreds and hundreds of thousands of outcomes, it may not be easy to list them all. Probability calculations don't need individual lists. We just need to know the number of them. And an example of what we're trying to do is to say, okay, if you play poker, you get a 5-card hand. And if you're dealt a 5-card hand, what's the probability of getting all spades in your hand? So you would need to know the number of ways to get all spades in a hand, and that would have to then be divided by the number of ways to get a 5-card hand. So instead we need ways to count without directly counting. So counting methods. The fundamental counting principle. Okay. And it basically says if you have an experiment with 1, 2, 3, all the way down, if you want to figure out the number of outcomes that are possible in your experiment, you'd figure out how many outcomes are possible in stage 1. So let's call it N1. And then you would multiply it by the number of outcomes in stage 2. And then you would multiply it by the number of outcomes in stage 3. And so on and so forth. As an example, some license plates used to be given by, or still are given by, 3 letters and 3 numbers. If I'm allowed to repeat letters and numbers, well, in the English alphabet, there are 26 letters that I could choose for the first slot. If I'm allowed to repeat them, then I can choose another 26 letters for the next slot. And if I'm allowed to repeat again, then I could choose another 26 letters. Similarly, for numbers, I'm talking about a single digit, so there are 10 possibilities for me, 0, 1, 2, all the way up to 9. And if I'm allowed to repeat, then I'll have another 10, and then I'll have another 10. And so the number of license plates that I could possibly generate this way is actually a really big number. It turns out to be 17,576,000. I certainly didn't count them one by one, but what I did was just use this idea of counting principles to allow me to do that. As another example, I could talk about the number of ways to list 5 books on a shelf. Okay, well, I've got 5 books. That means I have 5 stages, essentially, in my experiment. The first stage, I have to decide which of the 5 books is going to be there. So that means I have 5 possibilities for that first book. But once I've decided on the first book, that means I have 1 fewer book available for the next choice. So that means I have 4 outcomes possible for the next. And once I choose that book, I have 1 fewer again. So that means I have 3, and then 2, and then 1. And so this turns out to give me 120. What mathematicians have done is they've invented a new notation, and it's something called factorial. And rather than sit and write 5 times 4 times 3 times 2 times 1, what they've done is they've invented, or they've come up with this notation. So if you're assuming that n is a positive integer, when you write n with an exclamation mark, that's known as n factorial. And n factorial means start from 1, multiply it by 2, by 3, all the way up in jumps of 1 until you get to your number. So the previous example, we had 5 factorial. It was 5 times 4 times 3 times 2 times 1. And it doesn't really matter if you write it from 1 up or from the last number down. Note there's a little definition here. We are going to define 0 factorial to be 1, just to make formulas down the road work out a little bit nicer. And note that whenever you have a factorial, you could always write your factorial in terms of a smaller factorial. And so what I mean by that, this could be written as 4 factorial. So if you wanted to, you could write 5 factorial as 4 factorial times 5. And what that does is it allows you to simplify things a little bit more. To try to take us to the next topic, what we're going to do is extend the example I did with the books there. So let's talk about the number of ways to list 5 books on a shelf from 8 books in total. We still have 1, 2, 3, 4, 5 books that we have to put in. But what's different this time is that we've got 8 to choose from in total. So that means we could choose any one of those 8 in the first slot. Once I choose any one of those 8, then obviously I have 7 left for the next book, and then I have 6 left, and then 5, and then 4. Mathematicians will look at this expression that I've got, and they'll say, you know what? It seems like there's a pattern here that just hasn't finished, right? 8 times 7 times 6, all the way down to 4. And mathematicians would say, oh, I would really love it if this would finish off 3 times 2 times 1. So it would be wonderful if there were a 3 times 2 times 1 upstairs, but there isn't. So I can put one up there as long as I put one downstairs again, because something divided by itself is 1. And writing this down makes mathematicians feel a little bit happier. They say, oh, look, this is 8 factorial divided by 3 factorial. What mathematicians then do is define this to be a weird new idea. They'll say capital P, not for probability this time, but for something that's going to be called a permutation. And they will put a 8 up top, a 5 down bottom. And what does this mean? This means this is called a permutation. And this talks about the number of ways to choose 5 books, or let's say 5 objects, from a group of 8. Now, it's exactly like what we did up top, where we just listed out 8 times 7 times 6 times 5 times 4. And the key idea here is that the order matters. It matters which book you put in the first spot. So in general, when we write this symbol, KN, with a permutation symbol, there's a way to calculate it. Whatever number is upstairs for n will go here upstairs as a factorial, and you could see that from the example above. And we want to put it in terms of the size of the group that we're choosing. So how does this 5 relate to that 3 down there? It turns out that 3 you would get by going 8 minus 5. It's whatever was left over. And so this is the definition. This is the number of ways to choose k objects from n in total, where the order matters. And as an example, you could say a club has 9 members, right? In how many ways can a president, a vice president, and a treasurer be chosen? You could think of it just by directly counting, but I'm going to try to show you with permutation. You could think of this as, look, I've got 9 objects in total to choose from, and I want to be able to choose groups of 3. So I would have 9 factorial, 9 minus 3 factorial. And here I care about the order, right? I need to know who's going to be the president, and who's going to be the VP, and who's going to be the treasurer. It very much matters who is doing which job. If you simplify this, you'll get 9 factorial over 6 factorial. But remember I said earlier that it's very much possible to write a big factorial in terms of little ones. So 7 times 8 times 9 times 6 factorial. So it's convenient for you to divide through these factorials downstairs. And you end up with 7 times 8 times 9, which is exactly what you would have got had you just started with the basic counting principles.